Welcome back to The Explainer. Today we're decoding one of the absolutely most fundamental and, let's be honest, sometimes pretty tricky practical skills in Edexcel A-Level chemistry. We're talking about the classic acid-base titration. Specifically, we'll be breaking down the reaction between hydrochloric acid and sodium hydroxide using phenolphthalein. So let's figure out how to really structure our understanding and secure those top exam marks together.
Okay, let's dive right into this. How exactly do scientists find the exact concentration of a completely unknown acid? I mean, it sounds a little bit like magic, but it's actually a highly precise lab tool called a titration. It's basically using a solution with a known concentration to figure out the unknown one. Let's see how the math and the chemistry actually come together to make this happen.
So, here's our roadmap for today's explainer. 1. The chemistry. 2. The practical method. 3. Titration calculations. 4. The exam question. And 5. Common mistakes. Section 1. The chemistry. What is actually happening in the flask?
Right, so whenever we look at a titration, we are fundamentally relying on a neutralization reaction. In this case, aqueous hydrochloric acid reacts with aqueous sodium hydroxide to produce sodium chloride and liquid water. But notice that absolutely crucial ionic equation right below it, H plus reacting with OH minus to form H₂O. The key detail to spot here is the stoichiometry. It's a perfect 1-to-1 molar ratio. And you know, this simple 1-to-1 relationship is actually the entire foundation for all our calculations later on.
Now, what's really interesting about this slide is how we actually see this invisible reaction happening. Since both the acid and the base are totally clear, we need a sort of chemical spy, an indicator. For strong acid, strong base titrations like this, phenolphthalein is the absolute star of the show. In an acidic environment, it is completely colorless. But as the environment becomes alkaline, specifically between a pH of 8.2 to 10, it turns a brilliant pink. The truly frustrating part? Finding that precise endpoint where a single drop turns the solution pale pink and it actually stays that way. I mean, we've literally all been there in the lab, accidentally adding that one extra drop and just watching the flask turn screaming magenta.
Section 2. The practical method. The Edexcel Core Practical 3 walkthrough.
Okay, let's walk through the meticulous setup phase. Step 1. You want to rinse your burette with the sodium hydroxide solution first. This removes any impurities or residual water that could dilute it. Then fill it up and record your exact initial volume. Step 2. Grab a volumetric pipette and a pipette filler to transfer exactly 25.0 centimeters cubed of the hydrochloric acid into a nice, clean, conical flask. Finally, add just 2 to 3 drops of your phenolphthalein indicator to that flask, and stick to that amount, because too much indicator can actually skew your results. With the setup done, here is the actual execution. You open the tap to add your sodium hydroxide slowly, constantly swirling the conical flask to mix the solutions. As you start seeing flashes of pink appearing and disappearing, you need to slow right down. You have to add the alkali dropwise, literally one single drop at a time when you're near that endpoint. The exact moment one drop turns the whole solution a very pale pink and it stays pink for at least 30 seconds after swirling, you stop. Record that final volume. Then you repeat this entire process until you get concordant results. And just as a reminder, concordant means your titre volumes are within 0.10 centimeters cubed of each other.
Let's pause here for some crucial examiner tips, because examiners absolutely love testing this practical knowledge. A great trick is to aim for a titre of around 25 centimeters cubed. This specifically reduces your percentage error. Always read the burette at eye level from the bottom of the curved meniscus, and make sure you fill it below eye level for safety. And the ultimate secret to keep in mind? Never include your initial rough titration when calculating your mean. Just leave it out entirely.
Section 3. Titration calculations. Let's get into the step-by-step math. Everything you do in titration math revolves around this single fundamental formula. Moles equals concentration multiplied by volume. But watch out, because there is a massive trap right here in the formula itself. In a chemistry lab, you're measuring volume in centimeters cubed, but for this equation, your volume must absolutely be converted into decimeters cubed. You do this by dividing your centimeters cubed value by 1,000. Do not forget that step.
Let's talk through a foundational example so you can see this in action. Imagine you have a known sodium hydroxide concentration of 0.100 moles per decimeter cubed, and your mean titre volume was 27.30 centimeters cubed. Step 1. Calculate the moles of your known substance. That's 0.100 times 27.30 divided by 1,000, which gives us 0.002730 moles of NaOH. Step 2, apply our molar ratio from the balanced equation. And this brilliantly illustrates why that 1-to-1 ratio we spotted earlier is so vital. Because the ratio is 1-to-1, the moles of our unknown HCl are exactly the same, 0.002730 moles. Finally, step 3, calculate the concentration of HCl by dividing those moles by the acid's original volume, which was 25.0 centimeters cubed. Dividing that volume by 1,000 gives us a final concentration of 0.109 moles per decimeter cubed.
Section 4. The exam question. Applying your knowledge to a past paper. Grab a pen for this one.
All right, so here is a real data table from a student's experiment. They pipetted 25.0 centimeters cubed of HCl into a flask, added phenolphthalein, and titrated it with 0.100 mole per decimeter cubed NaOH. I want you to focus right in on the titer column. You got the rough titration followed by titrations 1, 2, and 3. Take a second and try to spot which results are concordant, meaning, of course, they are within 0.10 centimeters cubed of each other.
Let's see how this data builds into a classic multi-part exam question. We need to complete 5 specific tasks. First, identify the concordant results and calculate the mean titer. Second, calculate the moles of NaOH used. Third, write the Ionic equation. Fourth, calculate the HCl concentration to exactly 3 significant figures. And finally, state one advantage of using a conical flask rather than a beaker. Let's solve this puzzle piece by piece.
Okay, here are the model answers for parts A and C. For part A, the concordant results were titrations 1 and 2 because they were both exactly 25.80 centimeters cubed. So your mean titer is simply 25.80 centimeters cubed. Notice how we just completely ignored the rough titration of 26.45, and we ignored titration 3 because 25.95 is more than 0.10 away from the others. For part C, the Ionic equation is just the standard strong acid-base reaction. H plus aqueous plus OH minus aqueous yields H2O liquid.
Now let's walk through the calculations in parts B and D. Step 1, moles of NaOH. We take our concentration of 0.100 and multiply it by our mean titer of 25.80 divided by 1,000. That gives us 0.002580 moles. Step 2, we state our 1-to-1 ratio, which means we also have 0.002580 moles of HCl. Step 3, we calculate the final concentration by taking those moles and dividing by the original acid volume in decimeters cubed, which is 0.0250. This leaves us with 0.1032 moles per decimeters cubed.
So, the crucial point here is formatting our answer perfectly. Because the question specifically asks for 3 significant figures, our 0.1032 rounds to 0.103 moles per decimeter cubed. It's a really small detail, I know, but catching those required significant figures is such an easy way to secure that final mark.
And finally, part E. Why on earth do we use a conical flask instead of just a beaker? Well, the slanted sides of a conical flask make it dramatically easier to swirl the solution vigorously without spilling any of it. If you lose even a little bit of solution during mixing, your entire calculation becomes inaccurate. It's a simple, practical technique that translates directly into a free exam point.
Section 5, Common Mistakes. The top 5 traps you need to avoid. Okay, let's run through this rapid-fire checklist of traps. Number 1. Forgetting to divide your centimeters cubed volume by 1,000 to get decimeters cubed. Number 2, accidentally including that initial rough titration when calculating your mean. Number 3, picking results that are not within 0.10 of each other. Number 4, rounding your decimals in the middle of your calculation. Always carry the full decimal places through on your calculator until the very final answer. And number 5, which is perhaps the most common trap of all, writing the wrong indicator color change. Remember, when your alkali is in the burette and the acid is in the flask, phenolphthalein goes from completely colorless to pale pink. Never write pink to colorless.
And just like that, you have completely conquered the direct acid-base titration, going from the invisible chemistry all the way to the final exam calculation. You know the method, you know the math, and you definitely know the traps to avoid. But I want to leave you with a provocative thought. You've mastered direct titrations, but what happens when a chemical reaction is simply too slow, or the solid won't easily dissolve, and you need to perform something called a back titration? Now that is a fascinating challenge, and it's exactly what we'll be breaking down in our next explainer. Until then, keep practicing those